Now we're going to keep the same time. But we're going to go look at different space points. And if you remember, this guy was correct to order h squared. Okay, so this is again exactly this. These are exactly the same ideas that we used last week when we looked at boundary value problems. The only slight difference is when I looked at the first derivative on the boundary value problem, I did something a little bit more accurate. I calculated not at t plus delta t minus t, but t plus delta t minus t. This would have been evaluated at minus delta t. You can do that in this case too, but it requires you calculating extra fields, so we're not going to do that. We're just going to use a simple first order update.
Yeah, how do you get the first order? I know where you get the second equation from.
Okay.
I'm kind of lost where you get the first
Okay, so let's look at a simpler context. If I just had dy dx is equal to f of x and y, for example, okay, then what would I do here? I'd say y at x plus dx minus y of x over, or y of x plus h minus y of x over h is equal to f. Okay? Now, does that look like the Euler update? Yeah? So that's all I did here. So this is just the same thing as the Euler update. Now, the difference is, if I think about it graphically, find a little bit. Let me just take a little bit of space here. If I think about it graphically, what's the difference? So here's a function y of x. So if I take this point minus this point, and I divide by the delta, I'm actually calculating the secant slope between those two guys. Okay? Now, if instead I take this point minus this point, then that secant slope is much closer to the tangent at this point. Okay? So what I did last week was I took this point minus this point as the approximation to the tangent here. What I'm doing there is I'm taking this point minus this point as the approximation to the tangent. It's not as good, but it saves me having to keep this point, which is now a whole field, not a single point. So that's why we're going to do that. Okay. So let me now, instead of writing these guys, okay, I want to replace these by this kind of notation, okay? So t at t and x I'm going to call t n m, okay, because I'm just going to essentially replace my x by n times h and t by n times delta t. Okay. So then what I'm going to do is take this equation, plug these things in, and rewrite things instead of functions of t and x at n and m. So then I'd have t n plus 1 m. Okay? And what does that mean? That means the temperature at time step n plus 1 and space point m. Okay? So that is equal to the temperature T at the earlier time. So what I've basically done here is I've taken this and replaced it by this. Now here, this is T n m plus 1, and this is T n m. Does that make sense? Because these are being calculated at discrete intervals. The time, No, that doesn't make sense. It's n plus 1 m. This is t n plus 1 m. This is t, this guy is t n m. Yeah? So I've got my first derivative on the left, and what I've done is I've taken the n plus 1 here, and I put the n over the right-hand side. Okay? And now I've got to put in these guys. So that gives me the dt. And this has to be multiplied by delta t, because these two guys had to be divided by delta t to give the partial derivative. Yeah? And now I need to multiply it by the second derivative of this being approximated by this. So there's an h squared on the bottom. And there we are, okay? So now that partial differential equation that we started with, that's on the top right, is now basically just a linear algebraic equation. Okay, so this is a linear algebraic equation that relates these t's at different points in this nm grid. Okay. Now, if you look at this, then if I know the temperature field at the time step n, then just like when I use the Euler algorithm to solve an ODE, I've got everything I need to know to calculate the temperature field at n plus 1. Okay, so this again isn't just an explicit formulation. So I can just, if I know the temperature field, for instance, at n equals 0, I've got everything I need to know to calculate the temperature field at n equals 1. And then if I've got the temperature field at n equals 1, I can calculate it at n equals 2 and step forward, just like we did for the ODE with the Euler method. The only difference is that instead of stepping forward one thing, I'm going to be stepping through this whole field of values. Okay. Now, the only thing that we need to notice now is that this can only work when m is 1, 2, up to m minus 1. We can't use this equation when m is equal to 0, because then this will be running off the bottom. We don't have the point m equals minus 1. The thing starts at m equals 0. And we can't use it where m is equal to capital M, because this one will run off the end of the plus m. Okay, so just like the boundary value problem, we can only use this for all but 2 of the points. Okay? At the other 2 points, we've got to use boundary conditions. So we need t of n and 0 is equal to 25. So what we're saying is that at the left-hand end, where m is equal to 0, we're going to put the temperature equal to 25. We know that because that's what the boundary condition says. It says that the left-hand end is being held at room temperature, while the right-hand end is being heated up to 100 degrees. So we know then that the Tnm is equal to 100. Okay? And we have that from our boundary conditions. And then the second thing I need is I need to know what the temperature field is right at the beginning. So I need T0 everywhere, which is 25. Okay. So that serves to completely close the problem. Those 3 lines actually define the solution to that partial differential equation with those auxiliary conditions, okay? So the auxiliary conditions are the 2 boundary conditions and the fact that the temperature is uniform at t equals 0. So those 3 things, the equation, the boundary conditions, and the initial conditions, So that's a complete problem statement. So now we can go ahead and actually solve that, and I'll show you a little program that we can use to do that. But why don't we take a break for about 10 minutes first, and we'll get it set up.
Before you erase that, where did you get this last equation from?
So I did that last, if you go back and look at your notes last week, so basically I do a Taylor expansion here, and a Taylor expansion here, and add them together. Okay, so then what happens is this guy is a plus, and this guy is minus. So all the odd derivatives cancel. So I land up with twice this guy, the first derivative, the second derivative, and then the next thing is the fourth derivative. And this thing starts off with order H4, 95. So if you go back and look at your notes, you see that I did that when I was doing the panel. What's S? Oh, you put the values in. No, I mean, this is H squared. Did it give you the right answer?
Yes.
Then you did it right.
Every time I do something,
Okay, so now you have to be a little careful. Now, that's a different problem, isn't it? Okay, so this is, okay, that's what you were talking, okay, yeah. You don't have, I mean, you can write it in different ways, because it's just a set of equations. So I think I wrote it in 2 over h squared plus 4 no h squared here. And it's exactly the same. Yeah, but you see, that's because I put it in later. You just have to make sure it's consistent. You only have to get the right answer.
What is this?
I mean, this is the right idea. I don't know whether it's exactly right. So I'd have to check more carefully. Yeah, that looks like it's the same. Okay. So what are you asking me? I think Ian's posted some solutions to some of I mean, you know, if it's working in 90%, I mean, I don't remember all the problems offhand, okay? So if you come to office hours this afternoon,
Yeah, so we're running. Wow, look at you. How did I look? Are you gonna be here recently? I don't know. Dude, you think, Manny? That guy's funny, the other, that black guy.
Family doctors out there. We're talking about the name. Yeah, you were in the hospital down there. The lowest show is out there guaranteed. Yeah, missionary, yeah.
Let me have a rough show of hands. Who wants to do office hours this afternoon?
We have a transport test on Wednesday.
Okay, so bearing in mind you have a transport test on Wednesday, who wants to do office hours this afternoon?
Why don't we do them on Thursday?
Yeah.
We can do it in class on Thursday. Would you rather do that? That's fine. I mean, what's that? Thanks, Ruth. I want you to be straightforward.
200 of us.
Okay. No, there hardly anybody has been showing up for class on Thursday. You're more than real space to yourself. But of course, you have to come at 8:30 rather than about 10 o'clock. But I mean, all I was going to say is if there's only a relatively small number of people who want to do office hours today, I'd rather just do it in my office as people come by. But if it's going to be a ton of people that's just going to leave my office jammed, then we'll go over to the student center. So let me just say this. I'll be in my office this afternoon at about from about 2 to 4 for you guys. If there's too many of us, then we'll go over to the student center and find some space there. Okay. So if you're looking for me, I should either be in my office, possibly in the lab, or over in the student center. Okay. So they're all pretty close to one another.
So Thursday nonstop?
No. I mean, so Thursday we do Thursday class, but I will do office hours for the Tuesday before the final if you want. Okay. So there'll be office hours this week, next week, and then the week before the final. The week before the final, I'll see if I can get us a conference room because there's usually a lot of people there. Okay, so now we want to be able to solve a PDE just like the one we were looking at. So there's this little set of programs for partial differential equations. This is the guy that last week I showed you when we solved the boundary value problem. So this is a guy that will solve a heat diffusion equation. So basically, it's set up to solve the problem that I've posed, okay? So it's setting the increment size to the 30 centimeters, which is the length of the bar, divided into however many steps we specify. So the program is allowing us to specify how many steps, how many time steps we want it to take, and how big the time step is. And then